And I understand that NASA also has projects beyond the Kepler mission, and we're going to talk about those. But first, Russ, I believe you brought a slideshow along, and you're going to show us a few slides to illustrate some of the stuff that Ames is doing. So let's go ahead and bring that up. Could we see the first slide, please?
Okay, so this slide shows that the questions of other worlds, other Earths, is a really ancient one. And all the questions that Pete talked about in the beginning, are we alone, are there other Earths out there, is at least 2,000 years old. So this is a quote from a Greek philosopher, Epicurus, who basically stated that there can be worlds like our Earth elsewhere in the universe. And this is amazing that in all the time between Epicurus and our age, 100 generations, we are in the generation, we're privileged to be in the generation that's answering this age-old question. So I think this is amazing.
And here's another slide. So what's this showing us?
So this is showing the fact that habitability depends on planet size. If a planet is too large, it retains too much of the primordial hydrogen gas and swells up into a gas giant like Jupiter, which is uninhabitable as far as we know it, or at least not habitable by life as we know it. And then if a planet is too small, like Mars, or smaller than Mars, then it doesn't have enough gravity to retain an oxygen atmosphere, again, rendering it incapable of supporting life as we know it. So there's about a slop of a factor of 2 around Earth size where a planet is considered habitable. And we call planets larger than Earth super-Earths that are between 1 Earth size and 2 Earth size super-Earths, and they're still habitable. And roughly when a planet gets more than 2 Earth size, we think it's no longer habitable. So,
okay, and there's another slide.
Another factor that determines habitability is how far the planet is from its star. If it's too close, then all the water evaporates. If it's too far, all the water freezes. So there's a region around the star called the habitable zone where habitable planets can exist. So Kepler finds what are called potentially habitable planets. Well, actually, it finds many planets, but one of its mission focus is to find habitable planets, or potentially habitable planets, which is defined by being roughly Earth size and inside the habitable zone. And one of the cool things that Kepler has discovered thus far is that about 15% of stars, or at least 15% of small stars, have potentially habitable planets in our galaxy alone. What that means is that basically for every human alive on Earth today, there is a habitable planet, or at least one habitable planet. So you can have a habitable planet.
I can have my own planet.
Yep.
Stake my claim now.
Your friendly neighborhood baker can have a habitable planet. You know, a little girl in China can have a habitable planet, all to themselves. This is just amazing.
These are candidates. These are planets that have not been ruled out as being able to support life.
Well, Kepler is determines the frequency of planets. So it didn't actually find 8 billion habitable planets, but it has determined that if if the statistics of all the stars are similar to what it has found, then in our galaxy there are more than 8 billion potentially habitable worlds.
It took a good statistical sample.
Yes, exactly.
That we can extrapolate from.
That's exactly what it's doing. So. And so in that sense, Kepler has been a wildly successful mission.
Okay, now here's another slide. This looks like a spectrograph.
So as cool as Kepler has been, one thing that it cannot do is it cannot determine whether a planet is actually habitable. It can determine that it's potentially habitable, but it cannot distinguish between a hellhole like Venus, whose surface is hotter than the inside of your oven, and a paradise like the Earth. In order to differentiate between them, we have to figure out what's inside their atmosphere. And the way we do that is by doing something called spectroscopy, which is spreading out light from a planet into its spectrum like a prism does, and then seeing patterns in that spectrum of frequencies of light that have been absorbed by different gases like carbon dioxide and oxygen and water.
So that means that you can aim your optical instruments at such a fine angle that it can pick out one tiny little planet, hundreds or thousands of light years away?
So
without interference?
Yes, there are several ways of doing that. You can do it with transits, because with transits you observe starlight passing through the planet's atmosphere. But this is very difficult to do, and maybe even impossible to do for small planets like the Earth. But if you can directly image planets, take a picture of a planet, then spectroscopy becomes easier, and then you can take its spectrum and figure out if there's water, oxygen on the planet, and whether it's habitable. And in particular, one thing that's very important to look for is oxygen. Oxygen is a biomarker, which is a fancy way of saying it's an indicator of life, because oxygen, at least as we know it, can't easily exist without life. On Earth, if life were to suddenly disappear, all the oxygen in the atmosphere will disappear in about 1 million years, which is a blink of an eye on geological timescales. So if we find oxygen on an Earth-like planet, we would be hard-pressed to explain it any other way than life. So,
okay, and let's look at the next slide.
So I mentioned that in order to take a spectrum, it's kind of difficult to do it with transits on small planets. So what I'm working on, and a lot of my colleagues, is on trying to directly image a planet, which means taking a picture of it. The main challenge there is that the brightness of a star is many, many times greater than the brightness of a planet. Our sun, for example, when viewed from far away, is 10 billion times brighter than our Earth. This is similar to the brightness difference between a firefly and a searchlight.
I understand that in the previous slide, the firefly was there, but you couldn't see it. Now that the searchlight is off, you can see the firefly.
Yep, absolutely. So the challenge there is to be able to pick out a little firefly circling around a searchlight. And not only that, but to do it from 10 or 100 miles away, because stars are so far away that the angle between the star and the planet is very, very small.
And there it is, the firefly itself.
Yep. So this is a very challenging problem, but technology has been maturing, and we're essentially capable of demonstrating this type of performance in the lab.
Okay, and I think you've got one more slide.
Yep. So this is a time scale of NASA missions which have to do with exoplanets. There's Kepler, of course, and then the next exoplanet mission after Kepler is something called TESS. It stands for Transiting Exoplanet Survey Satellite. And it's a small mission, even smaller than Kepler, and it's a transiting mission, which means it looks for dimmings of the star rather than directly imaging the star, just like Kepler does. And the main difference between TESS and Kepler is that TESS will be looking at nearby stars and all over the sky, whereas Kepler was focusing its gaze onto a single field of view. TESS won't be able to get to quite the planets as small as Kepler was able to, but it would be able to look all over the sky. The next one after TESS is the James Webb Space Telescope. It's usually considered to be the successor to Hubble. It's a big general-purpose telescope that does many more things than exoplanets. Basically, does everything. But it can do things related to exoplanets also, like transits, and it also has can also do limited direct imaging as well.
Does the success of each mission determine what you do for the next mission? So you take your results and decide what to do next?
In some respects, it's more the science that drives the missions, and what the state of the science at a given time. And then looking towards the future, in my opinion, the domain of direct imaging missions. So EFTA is also going to be a multi-purpose telescope, but putting a direct imaging instrument is under consideration for it, and it won't quite be able to get down to Earths, but it would be able to get to larger planets, and maybe if we're lucky, it could bag a few Earth-sized planets.
Maybe I could add something about EFTA. This is an example of economy in the U.S. government. These were leftover telescopes built by the national security community. They were used to look the other way, to look down, and they've donated 2 of them to NASA. So we might be able to save a lot of money. The taxpayers already built them, and we use them for astrophysics.